In 2007, the European Space Agency launched a satellite carrying a particularly unusual payload, 3,000 living tardigrades. These microscopic animals, barely half a millimeter long, were placed directly in open space, unprotected, and exposed to the full vacuum of space, extreme temperatures ranging from -200 to +150 degrees Celsius, and lethal doses of both cosmic radiation and UV solar radiation. The experiment lasted 12 days. When scientists recovered the tardigrades and rehydrated them, 68% were still alive. Some of the survivors had reproduced in space. A creature that can survive direct exposure to outer space is not just interesting, it represents a fundamental challenge to our understanding of the limits of life. Our mental model of life's requirements is built around what we know life needs: liquid water, a source of energy, protection from radiation, a stable temperature range, and atmospheric pressure. Space violates every single one of these requirements simultaneously. The vacuum of space instantly causes liquids to boil away. Temperatures fluctuate hundreds of degrees between shadow and sunlight. Cosmic radiation shreds DNA. UV radiation destroys organic molecules. There is no air pressure. By every parameter we associate with biological survival, space should be universally lethal to life. Tardigrades rewrote this assumption entirely. They did not survive by being protected, they survived by fundamentally changing their biology. When a tardigrade encounters environmental extremes, drought, heat, freezing, or radiation, it enters a state called cryptobiosis by expelling nearly all the water from its body and replacing it with a protein called tardigrade-specific intrinsically disordered proteins, or TDPs. These proteins form a glass-like matrix around the tardigrade cells, vitrifying them in a state of suspended animation where all metabolic processes stop completely. The tardigrade is not sleeping, it is not alive in any conventional sense. Its cells are not functioning. Its metabolism is zero. It becomes a biological glass bead capable of surviving conditions that would destroy any living tissue. When rehydrated, the TDP matrix dissolves, the cells resume their positions, and the animal walks away as if nothing happened. The DNA repair capabilities of tardigrades add another dimension to their resilience. Radiation exposure, even at non-lethal doses, causes significant DNA strand breaks in most organisms. A dose of 1,000 Gray of radiation kills humans, the lethal dose is around 8 Gray. Tardigrades can survive doses of 57,000 Gray. They achieve this through a protein called SUP, damage suppressor, which physically wraps around DNA like a protective shield and reduces radiation-caused DNA strand breaks by approximately 40%. Even more remarkably, when radiation does cause DNA breaks, tardigrades appear to have exceptional DNA repair mechanisms that can reconstruct functional chromosomes from fragments that would be irreparably scrambled in any other organism. Tardigrades have been found in environments that should make life impossible: Antarctic ice sheets, boiling hot springs at 151 degrees Celsius, the deep ocean at depths of 6,000 meters, the Himalayas at altitudes over 6,000 meters, and naturally dried environments with essentially zero available water. A sample of dried moss collected in 1948 was rehydrated in 2016, 68 years later, and the tardigrades inside recovered successfully. They can survive pressures up to 6 times that of the deepest ocean trenches. They have been frozen at -272 degrees Celsius, just 1 degree above absolute zero, the theoretical limit of coldness, and survived. Life, in the form of tardigrades, exists at every extreme the planet can produce and some that only space can provide. The discovery of tardigrades in space has serious implications for astrobiology, the study of life beyond Earth. Panspermia is the hypothesis that life may travel between planets aboard debris ejected by asteroid impacts. If bacteria and single-celled organisms can survive the journey through space, as experiments suggest some might, then life could potentially be distributed across solar systems. Tardigrades demonstrate that complex multicellular animals, not just simple bacteria, can survive space exposure. This raises the possibility that if life exists elsewhere in our solar system, in the oceans beneath Europa's ice, in the subsurface of Mars, in the atmosphere of Venus, the barriers to its existence are far lower than we previously assumed. Tardigrades do not care about our definitions of life's limits. They evolved in a universe of extreme pressures, temperatures, and radiation on a planet that has repeatedly tried to kill everything on it, and they simply refuse to die. What makes them significant is not just their individual resilience but what they tell us about the robustness of life as a strategy. Life is not fragile. Life is aggressive, flexible, and extraordinarily creative at finding solutions to environments that should be impossible. If an animal the size of a grain of sand can survive outer space, what does that say about the likelihood that life has found a way in the frozen oceans of moons orbiting gas giants? What does it say about what might be living in conditions on Earth we have not yet looked carefully enough to find?